All right, I'm Kevin. We're back with another CS16B Spring 2018 Midterm 1 problem walkthrough. And so now we'll work on problem 2, what it do. We'll cover both parts A and B together. So part A asks us, consider the code below. We have public static int f takes in an int x. And if its x is 1, then we'll return 1. Otherwise, return 2 times f called on x divided by 2. So this is a recursive problem. All right, so now what does it want us to do? Describe as succinctly as possible what this method does when executed for all possible values. Okay, they're really making that bold, so we want to consider everything x could take on. If the behavior is different depending on x, describe the behavior in every interesting case. Remember that integer division in Java rounds down, i.e. 3 divided by 2 equals 1. All right, let's see. So I like to kind of go about this for like all possible values of x. As with like writing recursive problems, it's helpful to think about different cases, right? So what happens when it's 0? I mean, there's no base case for that, right? What about if it's 1? There is base case there. So if it's 1, oops, let me actually just draw it out. 1 will end up yielding 1, returning 1. How about 2? Well, we'll not use the base case. We'll use 2 times f, 2 divided by 2, so 1. So 2 times the 1 case will be 2. 3 will be 3 divided by 2. That's floor division or rounding down, which will give us go back to the 1 case, and I will still return 2. Then writing out 4, so we'll do 2 times f of 2, and we know f of 2 return 2. So it'll be 2 times 2, which is 4. How about 5? All right, 5. I can do this. 5 is 2 times the result of f of 3 divided of f of 3 of f of 5 divided by 2, which is going to be 2. So that will still give us 4. And you can kind of see the pattern that's forming as we get to larger numbers. So for example, if we do one more, if we do 6, that will be calling f of 3, and f of 3 return 2. So 2 times 2 is still 4. All right, so it seems like for values greater than or equal to 1, for x greater than equal to 1, this seems to compute the return the largest power of 2 smaller than x. That's the way to say it. Largest power of 2 that is less than x. But like we said, we should probably go through all the possible values or just consider some of the interesting cases. So what happens when x is not like huge? I think it'll still work, unless there's like some weird things when you get to like the very end of the int spectrum, but it should be fine in this problem. How about x equals 0? That's a tricky one. So let's see. If I pass in 0, it's not the base case because x is not 1. And now if we look at the recursive case, we do 2 times f of 0 divided by 2. So 0 divided by 2 will still be 0. And if we do that again, we'll just be calling f of 0 on f of 0 on f of 0 forever, which is also not very good. How about f of negative 1? Well, negative 1 goes, let's see, not the base case. And that will just truncate. That will do some division. And it looks like that will also give us infinite recursion. So for all other x, infinite recursion, or Java, we might say it gives us a stack overflow exception for the same reason that you might get a recursion depth exceeded in Python, because programming language will stop you from harming yourself. All right, so that's 1a. Now 1b asks us to consider the code below. Public static void g takes in an int list x. If x is null, return. Otherwise, call g on x.rest and then assign x.rest equals x. Draw a box and pointer diagram. If objects are not referenced by anything, you may omit them when drawing if you prefer. Endless definitions on page 7, but I remember it. If G never finishes because it gets stuck in an infinite loop, write infinite loop. Okay, so box and pointer diagram. Let's just go ahead and get started. L is going to be an int list of 3, 4, 5. So what that looks like is this. So we'll have, oh my, let me draw this site. Hard to draw with your finger. 3, 4, 5. So we have 3, we have 4, we have 5. Okay, so that's the int list of 3, 4, 5. Calling G on L. I think the way to do this is just kind of walk through that recursion step by step. So we just do exactly that. We'll start, okay, so we're not there. Then we call G on x.rest. So we're going to call it on that. We're going to do the same thing. Going to call G on x.rest. And the way you do that is like these two steps I've been doing is I take a look at what's in x.rest, or in this case, like starts with L, then we look at L.rest, then L.rest.rest, and we're just following those pointers as we go. So because we're not assigning, we're not actually changing anything, so we want to follow the pointers. All right, let's see. So now that when we get to this last node with 5, so it looks like x is still not null, so we're going to call G on the null pointer. So we'll just represent it like that. Now when we pass in x being null, we'll just return from that case. So we'll go back to our previous call. And our previous call will pick up where we left off and execute, let me write that a little more closely, x.rest equals x. So x.rest will no longer equal that pointer. It will be a reference back to itself because this is like x, right? So whatever x pointed to, this little arrow over here will just point back to itself. And that's what we'll set x.rest to. Now that we've finished that, we'll jump back to where we were called from. And now we want to finish off this line as well. X.rest equals x. So again, we ask that same question. What's x? X is this reference to the node containing 4. Then we will replace that pointer with a pointer back to itself again. And the same pattern seems to be happening for 3. And that will be our final product.